Great. Okay. Good morning, everybody, and I'm really happy to see all of you today. And thank you, Alex, for excellent organization of this workshop and so for the introduction. Well done. Yeah. And I would like to start. So today, my talk is actually introduction to high-efficiency video coding and high dynamic range. The agenda of my talk is as follows. First of all, I would like to give a very brief overview of block-based hybrid coding, followed by more detailed introduction of HEVC, including codex comparisons. Then I would like to make introduction of high dynamic range. And finally, I would like to present some future perspectives beyond HEVC. Yes, you already know there is already standardization efforts related to the future video coding beyond HEVC, and also provide some additional codex comparison results. So before I start, I would like to ask the audience how many of you are actually in the field of video compression. I just would like to understand, like, how deep can I... Okay, so it's not too many, but fine. Okay, so I will not provide very detailed technical details because I think anyway, we don't have enough time because tutorial for HEVC, in the past I conducted such tutorials with my colleagues and it took 4 hours. So in 20 minutes for HEVC and something like 20 minutes for HDR, we definitely cannot cover all aspects of this new standard, but I would like you anyway to introduce to new tools, and I'm sure that this information will be beneficial for you. Okay, so just a very brief overview. So who can tell me actually video compression goal? Somebody? Yeah, I would like the audience also to participate a little in the tutorial. What are the video compression goal? Yeah. Okay, so we would like to efficiency, let's say, condense visual data, right? While minimizing the loss of visual quality due to the compression, right? So this is actually one of the video compression goals in general. And why we need to compress video? Yeah? Come on, wake up. I'm sure you know. Yeah. Huh? Yeah, exactly. So we would like to reduce the storage space, reduce transmission delivery bit rate. Excellent. Okay, so hybrid video coding. What's hybrid video coding? First of all, block-based video coding, block-based hybrid coding. It refers to division into blocks, right? And then performing some kind of prediction, either intra or inter, followed by transform coding. So this is actually the main step of block-based hybrid coding. So we have a current picture. We have some particular block. We would like to find the best match. For example, it's really like a schematics presentation. So we would like to find the best match in the previous picture, right? We perform the search and then we get the residual, okay? After Motion compensation. Sometimes the things can be more complicated, so we find the best match not in the previous picture, but in another previous picture, and then we find the residual, which should be minimum, yeah? In order to reduce the bit rate, and after that we perform some kind of transform, such as DCT, discrete cosine transform, actually for converting spatial domain pixels into transform domain coefficient. So up to now it's a really simple approach. Finally, we apply quantization, for example, scalar quantization, just dividing by a number, and by such a way reducing a number of transform coefficients, reducing high frequencies. So the goal is actually to adjust the bitrate, the desired bitrate versus fidelity, and to remove subjectively irrelevant details. For example, some small movements like movements of leaves, which can be less important, yeah? And by such a way, of course, reduce the overall size of the file and the transmission bitrate. So let's talk about high-efficiency video coding. Do you know this guy? Huh? Now, this is actually Jevons, and there is quite known paradox which called Jevons paradox. So what does it paradox tell us? The efficiency with which a source is used tends to increase rather than decrease the rate of consumption of that source. And this is exactly what we see today in video compression, right? Initially, it was, to the best of my knowledge, it was intended to oil production, but things changes, yeah. Okay, so what we see today, according to the recent Cisco report issued just 2 months ago, I think, the IP video traffic will be around 82% of all consumer internet traffic by 2021, which just something like 3-4 years from now. And today, we see different kind of content, right? For example, dog TV. So those of you who have dogs can actually register, subscribe them to some kind of dog channel, and they can actually enjoy their favorite movies and series, yeah? Did somebody see some kind of dog TV channel content? Like what the content is? Somebody knows? No, normally it's dogs, like dogs would like to see dogs, right? So this dogs playing around, and the same for cats. So cats also don't stand behind. So we have today really like a lot of different content, which of course was not existing like 10 years ago, of course not, yeah. So for enabling high quality video services, we would like, we need efficient compression techniques, yeah, especially for 4K and 8K resolution. Actually, one of my dreams, and yeah, it's have some kind of a room in my house where instead of walls I have displays. So I would like to go inside, switch a button, like press a button, and then go to, for example, appear in the beach or appear in the forest. I really would like to see when it happens. And I think it's not so far from now, yeah? So maybe 10 years, who knows? Okay. So in 2010, I suppose many of you know, HEVC and MPEG organization established so-called joint collaborative team on video coding, which is abbreviated by GCTVC, and issued a joint call for proposals, which is called CFP. 2.5 years later, we get actually high-efficiency video coding standard. So first version of the standard was issued in 2013, which is already 4 years ago. Second version, just 1 year later, it addressed readiness tensions with increased quality, subsampling rate, etc., scalable extension for providing scalable coding, and multi-view extension. And finally, 2 years ago, we get a 3D extension, and 1 year ago, we got a HEVC version 4, which is actually screen content coding extension, which allows to compress screen content in a very, very efficient way compared to other methods and compared to some previous approaches. Now, I would like to emphasize that the scope of video coding standardization is quite limited, so only restrictions apply on bitstream and decoding process. So this is actually the things that are standardized. So this allows actually optimization beyond the obvious. It permits complexity reduction for different implementations, and of course do not provide any guarantee of the quality. So this is very, very important to understand. This is actually a scope of standardization efforts. Now, let's go to HEVC. One of the very important tools of HEVC refers to block structures. Yeah, we have in HEVC variable block sizes starting from a grid so-called coding tree units, so CTUs. You see them here, consisting of coding tree blocks. Now, these coding tree blocks are fixed sizes for Luma and for Chroma, and they are typically have a size of 64 on 64 pixels, but can set also to lower sizes. Here you can see a lot of different coding tree blocks, and these blocks are processed in the raster scan order, exactly as you can see here. Now, the coding tree blocks is actually a root of the coding quadtree structure, right? And the traversing of this coding tree structure is performed in so-called Z-scan order like this. This has especially big advantages for compression. Now, this approach is very important for larger resolution images, such as 4K. And by such a way, we can easily adapt block sizes. Yes, you can see here, this is actually one area of the big picture. And you see a lot of partitioning. I will deep into more details now. Now, the coding block which you have seen before can be split once into so-called prediction block partitions and recursively into transform blocks by using residual so-called quadtree, RQT. And the transform sizes varies from 4 on 4 to 32 on 32. So you can get here a lot of different variation, and by such a way you can really get significant performance. And we will provide you also with some results, experimental results in a couple of minutes. Okay, so here you can see, for example, splitting to depths of 3. You see 3 different block sizes. And overall, you can get here, I don't know if you see the pointer, but overall, you can get here 10 transform blocks. So it's once split into prediction blocks, then recursively so-called transform blocks by using the residual quadtree. And here you can see some kind of example. In blue, you see a Luma coding block and blocks, and in red, you see Luma transform blocks. So you can see all these blocks on the picture on your left. Okay. Now, we have a lot of different partition modes. So these modes are used only for interprediction. This is actually so-called asymmetric motion partitioning. And the modes on your left side refer to n on 2n and n on n, actually refer to intra-prediction. And what is important also to note that prediction block can be merged, which also provide quite significant savings. Now, let's look at the test. So all this approach with having quadtree and RQT provided significant gain. So if we allow in our encoder to vary CTU sizes from 8 to 8 to 64 on 64, we get a very big gain of up to 25%, which is really a lot. So this block structure provided one of the significant advantages of HEVC over AVC. And this is very important to understand. If we look here to allowing, here's the result for allowing different U sizes, the same. If you allow to vary the U size up to 32 on 32, again, you get the best gain of up to 17.5%, which is also very significant. And finally, the PU units, prediction units, if you allow all available PU unit sizes and you make the encoder to choose the best possible prediction mode and choose the best possible variation which leads to best prediction, we get up to 32% gain. So this is also very, very significant. Now, let's talk about interprediction too. Interprediction in H.264, I suppose some of you know, has quite many drawbacks. Yeah. So one of the drawbacks is it provides an efficient range of supported block sizes. For high resolution, it was not so convenient. Let's say HEVC originally was not designed for 4K, yeah, and for 8K. It was designed for, let's say, HD and plus minus similar resolution, but definitely not for so big resolution like 4K. And as a result, also, there was not sufficient number of interprediction direction in H.264, right? The planar prediction in AVC was not so good designed, and we have also different inconsistencies across block sizes. All these drawbacks, which you can see here, was overcome in HEVC by providing very important tools. So one of the tools was actually one of the approaches, let's say so, was computing reference samples with increased accuracy of 132 PEL by applying bilinear interpolation. And also we get much more prediction direction modes. So we get 33 directional modes, right? We perform some additional steps like reference sample smoothing. We perform boundary smoothing for getting better prediction. And prediction modes are actually unified across all block sizes. So by applying these tools, we actually overcome most of the AVC drawbacks. Here you can see an example of different direction. We have 33 direction plus planar prediction mode and plus DC prediction mode. For chroma, we have just 5. So we have planar, DC, horizontal, vertical, and it can be also the same directional mode as Luma. Now, regarding the interprediction, yeah, predicting from previous pictures. So HEVC improves motion compensation by applying quite many, let's say so, different efficient tools such as asymmetric motion partitions. It provides a reference picture set which allows to simplify the decoder picture buffer management. We have so-called advanced motion vector prediction. We have a block merging. We don't have time to get into details. If somebody wants to get more details, he can speak to me after the presentation. So all of this tool provide also quite significant results. Finally, we have in-loop filter. So we have the blocking filter, which you're also familiar with it from HEVC. And in addition to the deblocking filter, which is much more parallelized related to HEVC. Yeah? I would like to emphasize that one of the main approaches in HEVC was to allow parallelize as many things as possible because of the complexity. Yeah? We would like to make the things running in parallel. So in addition to the blocking filter, we have in HEVC so-called sample adaptive offset filter, which allows to individually map edge offset values as well as band offset values. And one additional thing that we would like to note, we have also some so-called special coding tools such as transform bypass, lossless bypass, and intra-PCM mode. What does it mean? We have a transform bypass in which Kabak context of transform actually directly applied to prediction error signal. We have a lossless coding by bypassing scaling, transforming, and loop filters. By the way, I would like to know the transform bypasses can be very efficient for images with sharp edges, flat areas, and some kind of screen content coding application. So for these types of content, this can be used in a very efficient manner. And finally, we have so-called intra-PCM mode, which allows to code the samples directly in case of emergency or if it's really required. So if you look at this diagram, we have three different types of alternative coding modes. Transform bypass, transform skip, so-called transform skip mode, and intra-PCM mode. Okay. One more thing is important to note that from respect of parameter set, we have SPS, so-called sequence parameter set, defining different parameters of video sequence, and picture parameter set, which are quite similar to those of H.264. But in addition, we have so-called new parameter set, VPS. It allows to describe overall characteristics of coded video sequences, including different dependencies between layers. So this was one of the new parameter set introduced in HEVC. Okay, regarding the parallelization, as I said, during standardization, it was very important. This was a very important issue, and it was discussed all over again. So as a result, we got quite many parallelization tools. One of the parallelization tools related to slices. So slices can be coded independent of each other, and in-loop filters can be disabled. Those in-loop filters which I described before can be disabled at slice boundaries. And dependent slices you hear with the dashed lines can inherit the previous entropy coding state. So this is quite convenient, and it's can be usefully used. An additional parallelization tool is styles. I suppose you're familiar with this tool. This is actually this rectangular regions of the picture. Okay. The slices are processed in the normal raster scan order. An additional tool, which is actually also provided very good results, is so-called waveform processing. The Kabak contexts are inherited from row above, so this is very efficient parallel processing tool. You can see here. So it's processing, and then the context is inherited, and so on, so on. If you would like to look at the performance of this tool, so this graph shows you the performance of tiles. Yeah. If you see here the peaks refer to providing just several one or more columns and many rows. So in such cases, you get a lot of losses. So you should wisely decide how many tiles you should provide, in which variations, like how many in column, in row, because it has a very big impact on the performance. And if you compare all coding tools, you can see that coding loss is actually quite big for tiles and slices, and very low for waveform processing. Region of interest, if you have some kind of region of interest within your video, you should use tiles polarization approach, because by such a way you can easily define this region by a corresponding rectangle and encode it accordingly. Okay, so regarding the profiles and levels, generally in HEVC version 1 we just have 3 main profiles. It's main still picture profile, main 10. The structure here is very well known as a so-called onion-like structure. So each additional profile includes all feature of previous one. Like this is the main still picture profile. The main includes all these features plus this, and main 10 all these features plus these features. In HEVC version 2, yeah, we have much more profiles. So we have 21 profiles, which is a very big increase from version 1. And this allows us to provide, to encode images and videos in different types of, different kind of quality settings. For example, for medical application or for any other purposes. So we have for Rex extensions, 21 profiles. For scalable extension, we have just 1, and for multi-view, we only have just 1. Now, regarding the results are very, very significant. So according to the verification tests, subjective evaluation, which was conducted already a couple of years ago, the average bitrate setting for UHD is up to 64%, which is very significant. Of course, it's compared to HEVC predecessor, AVC. And if you look at average bitrate saving relative to HEVC main still picture profile, so again, we get very big savings. And if you compare for JPEG, it's 44%. You can see it here. It's more, all these codecs are compared to JPEG. So HEVC provides the best bitrate savings of 44%, and AVC only 33%. Now, let's talk about outlook of HEVC. As you have probably noticed, HEVC got a quite nice deployment in last year, and the outlook of HEVC is currently extremely positive, right? We see increase of deployment, and according to the recent report issued by Gary Sullivan, HEVC is actually really get big deployment in the last years. Currently, we have essentially all 4K television supporting HEVC. We have Ultra HD Blu-ray disc supporting HEVC exclusively for UHD content video. We have Ultra HD forum specifying for 10 bits HEVC exclusively. In addition, we have can say that HEVC is a key element of the HDR video rollout, right? It allows us to get HDR on our TV screens due to significant improvement in the video compression. We have video-ROM Blu-ray disc supporting HDR videos in HEVC. We have Dolby Vision HDR technology providing enhancement of HDR10. So we can see all over that HEVC really get a big boost in deployment. And yeah. Now, when we talk about high dynamic range, we actually talk about more than 16 f-stops, when a change of 1 f-stop corresponds to doubling of the amount of captured light. And if you look at this diagram, it's nicely represent the HDR display compared to the human visual system. Now, as many of you know, our human visual system consists of rods, right? We have some kind of 100 million photoreceptor cells, which is, and cones, which are referred to color, we have just 6 million cells. So from this perspective, our human visual systems are much sensitive to luminance and to chrominance. And we can actually present our human visual system by so-called contrastivity function, which is shown like that. By the way, I finished the section of HEVC. Somebody have any questions? Because I move straight forward. We don't have enough time. I move straight forward to HDR. Regarding HEVC, somebody have some question?
I have a question regarding the scalable HEVC.
Yeah.
Do you have any implementation or deployment?
This is a really good question. Actually, I know that some companies are working on that. I don't want to publicly declare that, but I know they're working on that, but I cannot specify specifically who really deployed. Look, during the HEVC deployment, this issue was taken much more seriously compared to AVC, and let's say essentially from the beginning, SHVC was considered because, you know, for AVC, it was not so deployed, it came too late. AVC standard was issued in 2003, and scalable extension of AVC was issued 2007. It came too late. I personally speak to some companies and said, I would like to, you know, introduce scalable video coding. You would like to design a system which you can use with scalable video coding, and by such a way significantly reduce the bit rates, make more efficient, you know, all this usage. And they said, why we need to change this? Like, we have systems that works. We don't want to take any chance. We don't want to have some kind of risk. So for AVC, it came too late. For HEVC, it was considered from the beginning. But let's say currently it's still not mature enough. Like I suppose, let's say next year, maybe in 1 or 2 years, we definitely will see some kind of companies using that. Yeah, yeah.
But Gary Demos demonstrated practical software motion compensated wavelet years ago. So which scalable future will get there first? Some still proprietary, nobody's trying to standardize it, motion compensated version of a wavelet system, or scalable HEVC, which will become real and commercially practical first.
I don't see wavelets becomes any commercial. Wavelets have been never used, let's say almost never used for commercial purposes, and I don't see that it will be changed. The reason for that is very simple, because companies have already existing infrastructure of you know, hybrid block-based techniques, and it will not be. They will not switch it to wavelets. Okay. I don't see wavelets getting some kind of special attention with this regards, and this also will not happen for the future video coding standard beyond HEVC. No. Okay. Okay, so let's proceed. We don't have much time left. So the contrast sensitivity functions can be also calculated, right? So one of the approaches, well-known approaches, so-called Barton contrast sensitivity function model, which has a lot of different values, and it's quite complicated. So this model was a basis of perceptual quantization techniques specified in the standard ST2084. And if we follow the peak of these contrast sensitivity functions, yeah, and we convert the contrast sensitivity function to contrast step, we can get some kind of just noticeable difference curves, which represent the smallest possible noticeable difference. And by such a way, we get to perceptual quantizer EOTF. You know, EOTF stands for electro-optical transfer function. And this was standardized in ST2084. So here you can see the PQ function right here, 10-bit. I don't know if you see it here, but this is the one. Here, the black line. Okay? It's going just beyond the Barton model. So you can see in the Barton model here is shown in purple, in dash purple. So it's just going just a little above the model. And by such a way, we get quite good approximation of the Barton model. Yeah, because Barton model is very complicated. We don't want to really standardize it as it is. We would like to get some more practical approach. So we have several standards addressing this perceptual quantization. One is ST2084. It's actually specified EOTF by using characterizing the HDR reference displays. We have ST2086. It specifies this metadata as well as ST2094. So this is main standard of SMTPE organization. In addition, we have a standard by ITU organization, which are quite known. BT709, BT2020, and BT2100. BT709 and 2020 do not define EOTF, but they provide some kind of guidance for parameters values for Ultra and HDTV television systems. The last one, BT2100, it's actually provide image parameter values for HDR television, okay? Provide recommendation for these values. And both PQ and I will just get here. And PQ actually standardized in this BT2100. So here you can see different color gamuts, comparison of BT2020 and BT709. You can see that 2020, which is refers to UHD-TV, is much larger. So we have much more colors inside. And as I said, PQ system as well as hybrid log gamma systems are both defined in the BT2100 recommendation. Now, for those of you who don't really remember what does it mean OOTF, EOTF, and or ETF, I just will provide a small refresher. So OOTF is electronic transfer functions, which convert the linear scene light into the video signal, and EOTF, it's function which converts the video signal into the linear light output. Okay, so you can see here, for example, if you have a scene light, we have a camera, so this is OETF part, and the decoding part is EOTF. So let's get back to BT2100. So PQ system in this standard was designed according to this model. Why, yeah, we have here inverse EOTF, and here we have EOTF. And one more thing that I didn't explain is OOTF. So what does it mean? OOTF stands for optical transfer function. It's quite important to understand what does it mean. The reference OOTF actually compensates for difference in tonal perception between the environment of the camera and that of the display. Okay, so if we have a light scene, we have OOTF, and we have a reference displayed light. So in this standard, which I addressed before, this one, for PQ systems, OOTF located in the camera, and for hybrid log gamma systems, it's located on the display side. So this is important to understand. This is the main difference between these two systems. The standard also proposed, let's say, make guidance for transforming one system to another. So if you just open the standard, you see what's written there. You can easily make a conversion between one system to another system. Okay, so these two systems are standardized and are provided in the BT2100. So to summarize BT2100, PQ specification actually can achieve a very wide range of brightness level according to this implementation, and in comparison, LG specification allows and provides a degree of compatibility with other legacy displays. Okay? So this is the main difference of these two systems. Now, very important topic now is actually what will be next. Yeah? We have seen HEVC, we have seen a lot of advantages of HEVC, we have seen HDR and scalable video coding, extensions. So what is next? Yeah, we're already standing in 2017, yeah. HEVC was standardized 4 years ago, the first version of HEVC. What's next? So for those of you who do not know, the process of standardization has already started 2 years ago. I would say it's not standardization, it's more like exploration. Standardization didn't start it yet, the exploration started 2 years ago. And it was decided that the future video coding standard should consider from the beginning 4K, HDR, high frame rate, SHEVC, drone video, 360 video. It was very important to understand at this stage that this should not be delayed. Otherwise, we most probably will not be able to see the deployment, as happened with scalable extension of HEVC. Okay, so currently, after two years after the explorational work on future video coding standard started, we have so-called reference software model, deploying already 25 different coding tools, which is quite a lot. So companies have been really actively developing this future video coding standard. Just a short list of some features which have been introduced. For example, larger block sizes, 256 on 256 so instead of 64 on 64. We have larger transform sizes of 64 on 64 instead of 32 on 32. We have some kind of adaptive transforms, overall 25 different tools, which is really a lot. And what about the performance, like what we finally get? So we actually get increase of up to 28% compared to HEVC, which is really, really impressive. So already we have a standard, not standard, sorry. Already we have a future video coding model which provides us a gain of 28% over existing standard, which is very impressive. Just like come back one slide before, here you can see a timeline of expected standardization process. So the standard is supposed to be finalized by 2021, which is still about 3 years from now. Okay? And this slide I just skipped also, so I would like to get back to it. Here you can see 65 different interprediction directions. So because we are talking about larger picture, larger resolutions, like 4K, 8K, possibly, yeah? So we would need more directional modes. Instead of 33 modes of HEVC, we already have here 65 modes. Okay. Now, also, I would like to present some additional tests. These tests have been conducted for different types of codecs. These are test sequences which vary from different sizes. And as a result, this is actually, we got this evaluations. If we take GEM is a future video coding model. In compared to HEM is a reference software model of HEVC. We see that we get a gain of 28%. Minus actually specified the gain. Okay, these values are weighted PSNR YV values, and in terms of BDBR, and minus is actually the gain. So if you compare future video coding model to HEM model, which is represent HEVC, we get 28%. If you compare it to AVC, we get 54% gain. And if you also compare it to different codecs, we also get, sorry, to AV1, not to AVC, we got 54%. And if you compare to VP9, we get 60% gain. Here, I don't present a comparison to AVC, but it should be around 40% gain. Okay? This is AV1, not AVC, sorry. And here in this column, you can see the overhead. So AV1 overhead over GEM is 127% in terms of weighted PSNR. AV1, I don't know if you are familiar with, but this is a codec of Open Alliance Media. And VP9, which was tested here as a AV1 baseline, which was fully based on VP9, is also huge overhead. So what I would like to emphasize by this table is that future video coding standard is on the way. It provides quite good result till now. Its complexity is quite significant. It's like 10 times larger from the encoding side compared to HEM, but I suppose it will be reduced. The work just started. We still have time to finalize the standard. So this is more or less that I wanted to say today, and I hope you will find this information beneficial.